Okay, so let's see how we treat this with math here. And what we're going to do, now we're going to think about our skills here. Let's pull this up and get it out of the way and look at what we're going to talk about. So first we're going to plot it. We're going to do our graphs, our all-important ability to analyze exit time, position time, velocity time, and acceleration time graphs. So let's draw those graphs for something dropping, okay? Because when something drops, you have the magic word for today, acceleration. Right? That's what Galileo was seeing, basically, when something speeds up or slows down. Speeds up / slows down. Right? So when you drop something, let's see what it looks like. So we're going to do the math. So at first, you just have to trust me that I'm drawing these correctly. So these are 3 kinematics plots. Therefore, they're all time on the horizontal axis. And we're going to plot position here. We're going to plot velocity here. And we're going to plot acceleration here. Okay? And we're going to do it for a piece of chalk that we drop. You ready? I'm holding it at the origin, and it sped up, and there it goes. It goes down like that. So let's draw that here. Let's see. So here's my chalk. All right, I'm going to drop it. It's going to go this way. And what we're going to do is have an axis, our x-axis, that it goes down. We're going to make it positive down. You don't always have to do positive up. You can have positive down. I'm going to put the origin there. All right, that's allowed. All right, so what does the position time plot look like? Well, you could think, well, it's probably curves, velocity increases, yeah, and it's got to be flat at the bottom. So I think I drew that last time. It makes kind of like a parabola like that. Okay. What, therefore, must the velocity do? Remember that the velocity is the derivative of the position, the change, the slope. So here it looks like it was 0. That matches what happens. I'll drop it from rest. And it increases like that. So there's your velocity curve. And let's see. So when you drop something, it has acceleration. Acceleration, which is basically the rate of change of v. Oh my God, we're not doing vectors. So just like velocity is the derivative or the slope of the position, acceleration is the derivative or the slope of the velocity. So here you can see when something drops, I'm just telling you now, we'll prove it later, when something drops, it has a constant acceleration. The velocity time curve is a line with a constant slope, so it just looks like this. Right? And I made it positive because we made down positive. If you were being more normal and you made up positive, then you would need to plot it as a negative constant. But here, it's a positive constant. Okay? Rate of change v, and we call this, we label it a, right? A in meters per second squared. Right? When you drop something, it's acceleration, and it goes like that. What was I going to say about that? So we can define it 2 ways. So now we're going to do things for acceleration faster than we did them for velocity. Okay? So you can define it with an interval equation. Remember, we had the delta t's. So you could say that A is delta v over delta t. Yeah, or you could say that's the final velocity minus the initial velocity over the final time minus the initial time. And you could do kinematics. Right? You could say, well, we can solve this for the final velocity. We'd say Vf equals Vi plus At if we just do some algebra. Right? So there's one of your kinematics equations. How much does velocity change? Well, it increases with acceleration if we have a constant acceleration. Right? So that's kind of the interval way. But remember, we also had the derivative way. What if your interval is really small? Like here, it's easy to say everywhere I go on this curve, the slope is the same. So if I say, what's the acceleration between these 2 points? Well, it's just that, rise over run. And if I do these 2 points, I get the same answer. And that's because acceleration is constant. But you could have cases where acceleration isn't constant, like jerk or something like that. So if you do instantaneous, you just use the derivative we talked about last time. You say A is dv dt. All right, this leads us all off into calculus. So we talked about how dv dt, it's just the fancy name derivative. It just means basically the same as this, just when you make delta t really small. And this is another thing it took them 2,000 years to figure out. Can something change on an infinitely small time? And they were worried maybe it can't, right? You can't move anywhere in infinitely small time. You can't be moving at t at a specific t. And the answer is you can. And that was the discovery of the derivative in calculus. And that was the philosophical thing they had to get over. All right? So that's just basically what acceleration is. It's like what I said in the word cloud. It's just the next level of derivative of the position. The first derivative is the velocity. The second derivative is acceleration. And the next derivative is the jerk. Okay? But we don't get into jerk. Okay?